last time, and I have mentioned a few of the properties. I'm going to try to prove a few things today. So the list of the properties I have in mind. First of all, well, one of the things I did last time was the cofactor expansion, all right? And I actually have a proof of the so-called cofactor expansion as it's derived from the definition I stated last time. But the proof of that is not terribly enlightening. It's rather technical, and it's one of the harder things in the entirety of my notes, so I won't be spending class time on that. But just rest assured, it is a non-trivial step to go from what I called the definition last time to those cofactor expansions that I described iteratively in general. That said, you can read it in my notes if you want. If you don't understand that particular part of the notes, it probably won't hurt you too much. In other math books, you might find a discussion in terms of what are called combinatorial arguments. I think it's sort of an explicit, you might say, tensor approach. But anyway, enough about that. So here are the main properties of the determinants. If you've got jth row of A, 0, that implies the determinant of A is equal to 0. Likewise for a column. And so, of course, in the items 2 and 3 here, I'm just saying that, if there exists even one J, all right, it doesn't have to be all J, but if there exists one J. 4, I will actually prove here shortly. It's the determinant of A1, A2, until you get to the kth spot. And then in the kth spot, I'll say little a, AK, plus little b, upper b, BK. Well, this is, sorry, and then keep going. All the way until you get to A sub n. So every column here is just A, except for the kth one, which has this linear combination. It turns out that the determinant has a nice property called multilinearity. You can pull the constant out, like that, provided you keep all of the other n-1 columns just the same. Okay, so this item number 4 is known as multilinearity. It's different than saying a linear transformation. Here we have linearity with respect to multiple inputs, so this is multilinearity. In particular, you can think of the determinant as a mapping from, let's say, Rn cross Rn cross Rn. All right, so n copies, and it outputs a real number. Okay, and what I'm saying in the blue right above here is simply that this mapping determinant is linear in each one of these vector entries. Okay, so this is called multilinearity. Ow. If you pinch your finger in the marker when you put the cap back on, it hurts. All right, you see 5.
I'll make sure I keep that as a note. We'll be testing.
Will you be tested on this? I don't know. Yeah, I'm going to come out in the middle of the test and be like, Christian, pull out your hand.
At least I'll get an A.
That's true. You probably could use that to flag out any grade you want to. Probably your ticket out of not doing homework the rest of the semester. Given the laws of this land, we'll see here.
Nah, I wouldn't do that.
I would pinch my finger to give me this class.
If I pass this class, I'm going to do it the right way.
I would chop off my finger to get an A in this class.
Oh God! Wow.
Okay, hold on, wait. Okay, can we stop the video for a second? Because that's just a little put on you too.
Moving on.
Wow.
if B is just equal to A such that you do a row swap, say the kth row swaps with the jth row, all right? The determinant of B is equal to minus the determinant of A. 7, if you construct B by doing a row addition, all right? So say you take A, and what you do to A is you replace, you take row K plus A times row J, and you send it to row K, then the determinant of B is equal to the determinant of A. And finally, 8, if you have any linear dependence, if you have any scalar, well, I'm a little less greedy. I say if the ith row of A is equal to some constant times the jth row of A, or I not equal to J, then the determinant of A is equal to 0. Of course, that's easy to understand given our starting point last class, right? Okay. All right, so to try to show you, I'm gonna prove number.
So that last row is, I'm sorry, that last property means that if there's any linear dependence, right?
Yeah, if you have any row as a multiple of another, game over. It's 0. In fact, last time you could see that if there's any linear dependence, right? If there's any linear dependence of the between the rows or columns, that means that the rows and columns aren't linearly independent, which means that it doesn't row reduce to the identity, which means that it's in fact not invertible, which means that the determinant is 0. Although I'm about to prove some of that a little more carefully today. So I'm going to prove number 4, and then I'm going to call it a day on these proofs. So here we go. The determinant of, I'm going to keep it short here, A1, and then all the way out to the interesting one, A sub AK, plus little b, big BK, da da da, AN. All right. Well, by definition, that was the sum I1 through IN equals 1 to n of A1, I1, and so forth, until I get to kth one, which would be A sub k, plus B sub k, I sub k, and then keep going until you get to the nth one, the nth column, the I sub nth coordinate of that. And oh, I forgot something. What makes the determinant, so alternating? So equalizing. Yeah.
Epsilon.
Yeah, the epsilon. I forgot. That's where the magic happens here. Epsilon I1, I2, da da da, IK, da da da, IN. Just emphasize they're all in there. Okay. And then what you do is basically just, what is this? Well, this is equal to A sub k plus B sub, A sub k sub IK plus B sub k sub IK, right? I mean, that's what this is by the definition of vector addition. Right, I'm just looking at the ikth component of that kth column, right? You're adding two vectors together, so by definition, that's how you add vectors. And so when you put that in here, right, when you put that back up into the expression, you get two sums, right? You get, and I can pull the little a out, right? In fact, let me do that in my I don't want to write everything here 15 times, so we just pull the a and b out here. You can do that, right? That's the definition of scalar multiplication. This is just an n vector there that I'm doing. And so what you're left with then is pull a out of the sum I1 IN, and then you got A1 I1 AK IK, and so forth and so on until I get to the nth one. keep forgetting my favorite symbol, epsilon I1, I2, in, and then plus the sum using properties of finite sums. But yes, but a little bit past where we prove things, but you shouldn't be too surprised when I tell you that if you can prove it for two sums, you can prove it for n sums that are put together, right? So here's that b, and okay.
I'm not sure it's all.
A1, I1, bk, I sub k, a, and the epsilon symbol, I keep forgetting it, right? I1, I2, in. Okay, but what is that? That's really nothing more than, this is exactly, by definition, the determinant of A1, AK, AN, plus the other piece over there is precisely, well, you got your B sitting out front there, and then you've got determinant of A1 concatenated all the way out to the BK, and then A's all the way to the end, A sub n. But I did this for an arbitrary column. I did it for the K column, so it just as well holds for K equals 1, 2, 3, all the way out to n. So you have linearity in each column. It's a lot of writing, but once you understand the formula that we made the definition of the determinant, multilinearity is really almost immediate from that formula. I mean, once I write this formula down, like I did last time, the fact that it's linear pretty much is just staring you in the face, because you have, the columns, components of the columns just multiplied and taken a sum, a linear sum, right? So like, finite sums basically linearity is preserved by the finite sum, and it's almost immediate, really. This proof is not that deep that I'm showing you, it's just a lot of writing. So, now, if you ask me, well, how do you see multilinearity in terms of the cofactor expansion? That I can't answer. That's not at all obvious. But there's like a long, deep gulf between this beautiful formula in terms of the epsilon symbol and that cofactor expansion, right? They're two very different ways of looking at the determinant. Oh, I guess since we did this much, can you guys tell me how to prove 5 if you're given 4? So suppose you're looking at the determinant of k times a.
So the sum.
That's k times a1, right? K times a2, k times an. A, right? You see what I'm saying? Because if a1 through an are the columns of a.
The sum of all, multiply all of them.
Right.
And then you pull out k to the end.
Right. You pull out. You use linearity in each column, right? Homogeneity in the first column, homogeneity in the second. So basically you pull out k times k, and then you got the determinant of a1, and which of course is just k to the n, determinant of a. There's 5. But 5's not bad once you have 4. So.
What letter in number 7 is under the R that is past the arrow?
Okay.
Okay.
So I'm saying you're modifying the kth row by adding the jth row.
Or a constitute.
Okay, so here's a fun thing. Suppose you take a square, right? And you have side length L, and then you expand each side length by 2, right? You know that the area of the original square, you get 4 times it over here, right? So if you think about what proposition, what 5 means for, say, an n-dimensional volume, what does it say? If you took an n-dimensional cube, right, and you doubled each side length, how much larger would the n volume be?
Choose the end.
Yeah, to the n, exactly. So, well, I'll just say that up right in the well. I think it'd probably be good for me to work on a short example to exhibit these properties for a numerical example. Basically, you can kind of use row reduction in a sense to do determinants in view of these properties. So suppose I have A equals to, let's see here, 1, 2, 3, 1, 1, 1, and 0, 1, 0. Okay, that's pretty simple. This may be too simple. I don't know. So if you do row operations, this would be like, let's say it's row 2 minus row 1 gives me what? 1, 2, 3, 0, minus 1, right? Minus 2, okay. And then you got yourself a 0, 1, 0. Let's see here. So row 2 plus row 3, and also I'll do row 1 minus 2 row 3. That gets us to what? 1, 0, 3, 0, 0? Minus 2.
If you add 2 row 3, you'll get a 1 there.
0, 1. I mean, I've cleared out the above the 1 in the lower row, right? Okay, and then finally, if you swap row 2 and row 3, what do you get? You get 1, 0, 3, 0, 1, 0, 0, 0, minus 2. Okay. I mean, there's different ways to go here. So here's the game you can play. So this is the, you can think about the determinant of A, right? So what do you call this thing? Row reduction 1, row reduction 2, row reduction 3, all right? So you can relate the determinants at each step. For example, going from here to here, I have the determinant of A is equal to the determinant of R1, right? That's using number 7 up here. All right, and then guess what? This one. Again, this one we have what? Determinant of R1 is equal to the determinant of R2 because again, I did row additions, right? What is it? Is there an arithmetic mistake or something, or there might be? Okay, and then this one. In this one, what happens here is the determinant. Yeah, right. Row swap gives you minus determinant of row 3, right? Now this guy is diagonal. Not diagonal, excuse me. This is upper triangular. Upper triangular. Okay, so we have a theorem that tells us that the determinant of R3 is just the product of the diagonals, which is really nice. So it's 1 times minus 2, which is minus 2. Sorry guys, I'm kind of oscillating back and forth between proving things about determinants and using properties, which I haven't proved yet, which is kind of bad pedagogy, but you can deal. I think you'd rather not have me spend 2 weeks of class proving all of these things in gory detail. The weird thing about determinant proofs is, while they're fun, they're kind of an aberration from the proofs in the rest of the course. Like they're not built on using arguments about spanning or linearly independent so much. They're mostly just arguments about a specific formula and how to work it out, which I personally love, but it doesn't kind of provide a basis for other thinking later in the course. So that of all the proofs worth skipping, these are the ones.
That makes getting determinants really easy, like say for something before, like R4 before R5.
Well, I didn't say determinants were easy. I'm just saying that.
Well, I mean, it makes it easier, like, to obtain it.
Oh,
that
well.
fact that, or am I
Sorry.
So determinant of A is equal to the determinant of R, I mean, I'm not disagreeing. Determinant of A is equal to determinant of R1, right? Which is equal to what? The determinant of R2, right? Which is equal to what? Minus the determinant of R3, which is then equal to what? Minus a minus 2. So the determinant's 2. And that's how you can calculate determinants using row reduction. Although I am not the most efficient person at this. People who are good at this can do it faster than I just did. And they have better notation than I use.
Yay, row reduction.
Did you stop at getting a -2 as opposed to dividing by -2 because you had the upper triangle?
Yeah, once I get to an upper or lower triangular matrix, then I can just multiply by the diagonals. Now, if you want to be really, really devoted to this method, yes, then I should clear out the 3, right?
But I mean, it doesn't matter, does it?
That doesn't cost me, I mean, whatever that is, that doesn't cost me changing the determinant. And then this,
Okay, you just do.
yeah, so what do you say, it's row 3 over minus 2, right? And that gets you to the identity matrix. Now, the identity matrix has determinant 1, right?
Right. So like, had you moved farther, then that would change your determinant.
Well, we just divided the matrix by -2. If we had not done that, it would still be like the determinant would be 2. So like, during the moment that you divide the entire matrix, the determinant's going to change.
We determined, we divided row 3 by minus 2, not the whole matrix. And by the whole matrix, that we would owe would be like a factor of 8 floating around.
Never mind.
It's okay. Anyway, so there's that. I'm gonna flip over to the projector here for just a bit because these arguments I want to show you, but I don't want to write down. Okay. Yeah.
So basically, you can't just multiply a row by a constant. You have to either add it at the same time.
No, you can multiply a row by constant, but it has a different effect, right? So like this one would have been, let's see here. So this is essentially, I guess we could call this thing R4, right? And you could say determinant of R4. How is that related to the determinant of the identity? What did we do to get from here to here? By -2. I covered that.
So if it's like multiplied by a constant, then you have to, you have to basically make sure that.
I'm trying to think if I need to, I think I need to. Logic here, I think I have to put 1 over that, so it's like, so -1 over 2, that determinant is equal to that. Which then would tell us the determinant of R4 was equal to -2, right? Which gets us back to here again.
Okay. So just when you multiply a row by a constant, you have to remember that in the determinant.
You have to be careful and use, how to use, let's see here, I want to be specific about what
See,
I'm
every single
telling
time
you
one
here.
of those properties is done.
Use property number, oh, come on.
7.
No,
Property number 7.
no, that one keeps the determinant the same. Aw, stink. You know, I've got the row swap, I've got the row addition, and then I just tell you that if one row is equal to another, then it's 0. I have failed to put in this list the interesting one, right?
Oh, no, it's good.
It's from 4 though. I mean, you can transpose this, right? It's also multilinear in rows because the determinant of A is determinant of A transpose. The columns become rows in the transpose, and so if you look at that, the determinant of, let's say here, row 1, k times row k, oh, maybe row j, let's say, row n would be what? It's k times the determinant of row 1, row j. Let's see, so what does that say? When we do a row operation, what are we doing? We don't, it's kind of backwards from this, right? Like, I took row, I took row what? I took row 3 and I changed it to what?
Negative 1/2.
Yeah, minus row 3 over 2.
So that means that you multiply by the opposite reciprocal of whatever you changed it to.
Yeah.
Okay.
So let's see here. I guess I could rewrite this as like, I could put the k inside here, right? And I could I guess I could pull it out over here with that. I don't know. I mean, we stop talking about it.
I mean,
that makes sense.
Okay.
I guess it's important to know so that we don't completely destroy the determinant unless we have another.
As long as you don't have to prove anything.
I mean, hopefully we don't.
Proofs I could show you actually. Not too hard.
Yeah.
All right. So. All right, so I've made some assertions. I want to give you a little bit, just talk through the justification of them, if nothing else. I think, again, just follow along with me. You don't really need to write anything down right here, just a moment. So first of all, the determinant of a diagonal matrix is the product of the diagonal entries. If you think about that, how would you prove that? Well, I've gone to some trouble to prove the cofactor expansion. And this is almost immediate from just applying the cofactor expansion. Oh, excuse me, not even that. I'm an idiot. Just use multilinearity on each row, right? Pull the D1 out, pull the D2 out, and so forth and so on until you get the determinant of the identity. But the determinant of the identity is clearly won by just using like the cofactor expansion. Pick your favorite row or column. It's easy to see that. Okay. By the way, an alternative definition of the determinant is that it's the unique alternating multilinear function such that that sends the identity matrix to the number 1. So you could define the determinant with those two properties. Anyway, that's a lower triangular or upper triangular product of the diagonals. And the proof is really just a cofactor expansion. So what am I doing? I'm doing cofactor expansion along, say, the top row or the top row, so I did here. And you can it's just explicit cofactor calculation. Yes?
So like when we're doing the determinant, we kind of like, it corresponds to like getting the identity matrix, correct?
Well, once you get to the identity matrix, you know that's 1. The determinant of the identity
Yeah,
matrix is 1.
but like,
so.
does this somehow correspond to the elementary matrix?
We're getting there. We're getting there.
Okay.
So the next proposition concerns elementary matrices like you were expecting. In particular, the determinant of the row swap matrix or the scalar multiple multiple elementary matrix or the row addition matrix. These have determinants -1, k, and 1 respective. All right? And those can be proved by just looking at the explicit elementary matrices and applying the cofactor expansion. All right? That's logic. Point number 1. Point number 4. Any square matrix B and any elementary matrix E, the determinant of E times B is the determinant of E times the determinant of B. That's sort of the genesis of this product rule for determinants, all right? That's what I'm about to describe to you, there's this wonderful, wonderful formula, which is extremely non-trivial to have. I mean, the truth that's, oops, wrong light. The truth that's in this formula, so the formula I'm talking about. Yes, Landon, you have a question while I'm erasing?
Well, I was going to ask, since it's like that determinant of EB, if you let B be the identity matrix and E be just like one step elementary matrix operation from that, that's why we get all this determinant, like with B proofs, like they're like the properties we just use. Is that kind of why it is? Or?
Yeah, you can see this calculation. I mean, this is how to prove some of those things I just said about, well, you could either prove them by a cofactor expansion calculation or by things I'm about to show you, but our goal at the moment in this discussion is to explain why the determinant of A times B is equal to the determinant of A times the determinant of B. If you think about what this equation I just boxed in here says, it's really quite awful. Think about how matrices are multiplied. Not entirely trivial, right? Think about how determinants are calculated. Also unpleasant, right? Even more so. And I'm telling you that to calculate the determinant of the product of two matrices, you can calculate the determinant of the first matrix and the determinant of the second matrix separately and just multiply those together. It almost seems too good to be true if you're just staring at these cofactor expansions. And yet it is true. It takes a little work to prove that. Yeah.
So that's an actual arbitrary matrix A and B, no longer, not just an
Right.
arbitrary.
So the proposition we're staring at right now is just your elementary matrix.
The one you wrote on the board is.
Arbitrary. Yeah, we're getting it. So E1 through EK are elementary matrices, and the determinant of the product of an elementary matrix is the product of the determinants of the elementary matrices. And so, you know, I have the arcs here. So once you have those, you get other things like a square matrix is invertible if and only if the determinant's non-zero. Well, think about this. If the determinant, suppose there are two cases then, right? Either the matrix is invertible or it's not. If it's not invertible, that means that there's a row or a column which is linearly dependent on other rows and columns, right? Which then means that the determinant's zero. Right? On the other hand, if the determinant, if the matrix is invertible, we proved earlier that means it's a product of elementary matrices, right? But the determinant of a product of elementary matrices is the product of the determinants of those elementary matrices. And I just told you that every elementary matrix has a non-zero determinant. I mean, they ought to, they're invertible matrices, right? But there you go. That proves then that the determinant of the invertible matrix is non-zero. I mean, here's the argument explicitly. If the reduced row echelon form of A is equal to the E1 through EK times A, then you just take the determinant of both sides. You get the determinant of the reduced row echelon form is the product of these determinants times the determinant of A. But if A is not invertible, this has a row of zeros, so it's zero, right? Hence, as these are non-zero, it forces that to be zero. And if this is the identity matrix, right, then this is 1, which then forces non-zero, 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 forces the determinant of A to be non-zero. So, once you write that formula down, what I'm saying is immediate. And then, so, that brings us to the main event. The determinant of A times B is the determinant of A times the determinant of B. Here's the proof. There's two cases to think about. Either the product, either one of A or B is, or both, is not invertible, right? So if A or B is not invertible, what that means then is the reduced row echelon form of one of the matrices or the other will have row zeros, right? So let's just suppose it's A. All right, so this guy has got a row of zeros, and if A is not invertible. But if you think about it, if you calculate, and of course we can also get to the reduced row echelon form of A from multiplying by these elementary matrices times A, like we talked about earlier in the course. So you can solve for A by multiplying by the inverses. That should be K. I don't know, excuse me, why I have just 3 here. This should be like K and dot, 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 right? Obviously.
I think it's two matrix.
Yeah. And then so we have reduced row echelon form times A. What happens when you take a matrix with a row of zeros and multiply it by another matrix? Well, on the left like that, you get
Column of zeros?
no, another matrix with a row of zeros. So yeah, like rows. These left multiplications do things with rows. So this also has a row of zeros in it, and consequently the determinant of AB is 0. So there you go. Determinant of A, 0. Who cares what the determinant of B is? The determinant of AB is also 0.
But you
shows-
only proved the
so-
zero case for a matrix of 3 by 4 instead of like by K. Not that you just
Well, K by K, but that's a typo. So yes, I mean it's easy to see how to modify this argument for the the case of not just three things. I don't know why I just have three. I think it's just maybe I was trying to be. I just have three things here. I don't know. I don't know. You should just demand your money back, please. So, but
Dollar the other case, the non-zero case.
0 equals 0. Hard to argue with, right?
Yeah.
On the other hand, if both A and B are invertible, that means that you can write each as a product of elementary matrices. Right? So AB is just this product of elementary matrices. And then you just apply the previous proposition about products of elementary matrices to determinants. And there you go. You're like, okay,
That seemed pretty easy, actually.
not too bad. Then you can say, what's the determinant of the inverse, right? Well, you can say lots of things. Let me put the projector away now that I'm through the part. I always regret when I spend actual class time to write these arguments out, because you can read them, you can understand them. Unlike most of the proofs I go over with, otherwise they don't really, as far as I notice, come up again. I think it's important to know where that formula comes from. I don't think it's good for the course in linear algebra just to tell you the determinant of A and B is the determinant of A times the determinant of B, as if it's some fact that comes from on high and you don't need to have an explanation for it. I mean, you should have an explanation for it, you know. It's not like something that can't be explained, or shouldn't be explained. Okay, so now that we have it, proposition. If A inverse exists, then the determinant of A inverse is equal to 1 over the determinant of A. Now these are the things that I think are nice test questions, right? How do you prove that? Well, what do you know? You know that A times A inverse is equal to the identity matrix, right? By definition of inverse. Right? Yes. You just suffered through me talking about the proof of the boxed identity right above, so let's use it. And the determinant of A times the determinant, determinant of A inverse is equal to the determinant of A times the determinant of A inverse using the identity boxed above, right? And that's equal to what? Determinant of identity.
The determinant of I is 1.
Right, determinant of identity is just 1. It's one of the basic things we know. So therefore, the determinant of A inverse is equal to 1 over the determinant of A. And there we go. Proved. See, that wasn't so bad.
That was really easy.
Yes.
Does that come into the proof at all when you're trying to determine the shortcut for the 2x2 inverse formula?
We'll get there. I'm not sure I'm going to get there today. I'm going to try, but I'm not sure we have enough time for me to get to that. I'll probably need about another 15 minutes past today, if I had to guess. I'm going to keep talking and see where we get, but. So at this point in the notes I have, I've got like a page of examples. I did some of those examples last time. I'm going to go on to the, what's called Cramer's Rule, okay? What is Cramer's Rule?
Spelled with A or spelled with C?
It's spelled, it's
like
Seinfeld has corrupted me. I have Seinfeld-based misspelling that sometimes you'll find in my notes. I tried to change it to C, and it's supposed to be C. But, yeah.
I actually just
I
know
actually
you.
thought it was supposed to be K.
Yeah,
I
no.
didn't actually know you misspelled it. I was just like curious.
I fixed it most places, I think. There may be a residual misspelling somewhere. Here's Cramer's Rule. So Cramer's Rule says the following. To solve, we're trying to solve AX equals to B for A invertible, and it's an n by n matrix, okay? And here's what it says. The solution is x1 equals to determinant of a1 over determinant of a. Now this a1 is not the a1 I was using earlier today. Here I mean something rather technical by a1 and a2 here, okay? I'll explain shortly. So what a sub k here in this context is I'm saying you take the kth column of A and you replace it with the inhomogeneous term, the B, okay? So A1, for example, is B, and then like column 2 of A, column n of A, and so forth, etc. The A sub j would be, you take column 1 of A, and so forth and so on until you get the jth column. And then in the jth column, you stick B. And then you just leave well enough alone, and you leave the rest of the coefficient matrix unaltered. I think you guys tend to use like a delta sub j or something for these in engineering. Is that right, Chris?
I think so.
Yeah. What are they called? Surely they must have a name. You guys like name calling now?
We like abbreviations and, you know.
Oh, abbreviations, notation, standard notations. Yeah, this is overrated.
Acronyms, we love acronyms.
Let's see here. So, what we need to what I need to show then is that claim is true. So how do you show something's a solution?
Plug it in.
Plug it in, right? And that seems like a reasonable suggestion, except that you shouldn't do that. So observe.
Hold up,
I'm telling you the straight, like, if you just try to straight check it, you won't like what happens. So here we go. AE1. What is AE1? Well, that's column 1 of it, right? In fact, all the way on to AEJ minus 1 is column J minus 1 of A, right? Let's see here. And so forth. So what's I don't know why I have written that there. Sorry guys, just a second here. I mean, I don't disagree with what I wrote and so forth. En is column n of NA, that's true. Who cares? I mean, yeah, right? So basically, I'm saying here, let x equal to xj, where xj is equal to, you know, determinant of aj over determinant of a. Okay. And what I say then is, if you look at a times the matrix e1, ej minus 1. X, where x is so defined. So this is a matrix equation, right? What do you get? You get, why do this? I mean, see, that's not the logic here. He's saying this is not quite the logic here, guys. I realize now. I mean, that's fine, but I shouldn't say let this be that. I mean, what I really should say, is okay, these are identities, right? Suppose X is a solution. All right, suppose X is such that what? AX is equal to B, all right? What happens when you multiply A times this matrix? I mean, everything except for the jth spot is simple, right? You get what? Column 1 of A. And so forth, right? Until you get to AX. And then you go all the way out until you get to column N. Okay, I'll skip the one before and after the jth spot because they're just the columns of A. But what is AX equal to by assumption if X is a solution? This is B, right? So what is it I have on the right-hand side here? This is, by our definition, this is precisely A sub j, right? So if X is a solution, then I have this identity for the solution. You guys see that? Now, how do I know the solution exists? I mean, A is invertible, right? So the solution, of course, is what? I mean, go back to the start. The solution is just X is equal to A inverse B, right? We're done. Yay! Except that, well, we're trying to do Cramer's Rule right now, so we don't want to do multiplication by inverse, right? So we have this identity, and then you take the determinant of both sides. What does the determinant of both sides tell you? You get determinant of A, determinant of this thing, right? And that's equal to the determinant of AJ. A little bit short on time, but this you can prove, right? In fact, this right here is exactly the jth component of the solution. And you can derive that from like the cofactor expansion if you like. Or if you believe your homework problem. By the way, I made an error in the last class. At the top row when I wrote that 3x3 determinant, I shouldn't have had EJ. I shouldn't have had E1, E2, E3 in the top row in the last lecture. You'll notice it when you do your homework. I have the correct thing in the homework problem. Anyway, that's xj, so there you go. That's it. That's exactly Cramer's rule, right? It says that the jth component of the solution is the determinant of AJ divided by the determinant of A. And there you go. That's Cramer's rule. But you notice what the linchpin of this proof is what? It's the product identity for the determinant. So if you try to prove Cramer's rule directly, you will suffer. Because to prove it directly is to recreate the proof of the determinant of the product of the private determinants. Which doesn't. Now, I owe you guys about another 30 minutes or so about determinants. Next time I talk about determinants, which will be after the test. I know you guys are excited about that. I will show you what's called the adjoint formula. We'll come back to where that 2x2 inverse formula came from and cast it in a more general light. My notes actually have the 3x3 case, and who knows, maybe I'll show you some examples. Anyway, I will shut up about that for now.